Hello everyone. Good day. I am John Teric, and today we'll be going to talk about the chapter 31 about alternating current. Alternating current, or AC, is the form of electrical power that drives most of the technology in our modern world. Unlike direct current, or DC, which flows in one direction, AC is continuously reverses its direction in a sinusoidal wave pattern. This fundamental difference has profound implication for how we design circuits, transmit power over long distances, and power our everyday appliances. Throughout this chapter, we will explore the mathematical representations, circuit behaviors, and practical applications of AC electricity. Our goal is to understand the principles that make alternating current such a powerful and widely used form of energy distribution. By the end of this chapter, you'll appreciate why virtually every device plugged into a wall outlet uses AC rather than DC. Before we proceed on our main discussion, let us first know the learning goals for chapter 1. Looking forward at first, how phasors make it easy to describe sinusoidally varying quantities. Second is how to use reactance to describe the voltage across a circuit element that carries an alternating current. Third is to how to analyze an LRC series circuit with sinusoidal EMFs of different frequencies. Fourth, what determines the amount of power flowing into or out of an alternating current circuit. And the last one is why transformers are useful and how they work. So imagine turning a radio in a classic car and asking yourself, how does this device select one specific broadcasting station from the multitude of signal traveling through air? The answer lies in the alternating circuits, which form the basis to receivers, transmitters, and virtually all wireless communication systems. The key question we must address is, how are AC fundamentally different from the DC circuits? In the current, voltage and current remain constant, making analysis straightforward using simple Ohm's law. However, in alternating current, both voltage and current continuously vary in time according to sinusoidal functions, which means resistors, capacitors, and inductors behave differently than they do with steady voltage. We shall systematically examine how each of these components responds to a sinusoidally varying voltage source, building our understanding from simple single component circuits to complex multi-element networks. This investigation will reveal why AC is superior compared to DC for power distribution, and why understanding AC circuit theory is essential for modern engineers and physicists. Most household and industrial power distribution systems worldwide operate on alternating current, or the AC, the form of electricity you access when you plug any appliances into a wall outlet. An AC source, formally defined as a device that supplies sinusoidally varying voltage, generates voltage that isolates smoothly between positive and negative values in a regular repeating pattern. This sinusoidal isolation is described mathematically by trigonometric functions, typically the sine or cosine, which naturally captures the behavior of AC voltage in time. The use of AC instead of DC throughout our power infrastructure represents one of the most important technological decisions of the modern era, championed by pioneers like Nikola Tesla and George Westinghouse. AC's superiority for a long distance power transmission systems from the ability to use transformers to easily step voltage up or down without significantly energy loss. Understanding AC sources is the essential first step toward analyzing how modern electrical systems function and deliver reliable power to billions of consumers worldwide. So a sinusoidal voltage might be described by a mathematical function written as V times T equals capital V times cosine of omega times T plus phi, where lowercase v represent the instantaneous potential difference at any moment in time. Capital V represents the maximum voltage amplitude. Omega represents the angular frequency defined as 2 phi times f, the ordinary frequency, and phi, which can be zero or non-zero, represent the phase angle. In the United States and Canada, commercial electric power distribution systems operate at a frequency of f of 60 Hz, meaning the voltage oscillates 60 complete cycles per second. For a resistor connected to this AC source, the corresponding sinusoidal alternating current follows the same frequency and can be expressed as I times T equals capital I times cosine of omega times T plus phi, where capital I represent the current amplitude. These mathematical descriptions form the foundation of for all AC circuit analysis and allow engineers to predict voltage and current at any instant in time. So to represent sinusoidally varying voltage and currents in a way that simplifies our calculation and intuition, we define rotating vectors called phasors, which are representation of complex numbers plane. A phasor diagram, as shown, displays these rotating vectors at a particular instant in time, with the length of the vector representing the amplitude of the sinusoidal quantity and the angle of the vector relative to horizontal axis representing the angle, denoted by phi. The beautiful instance of the Pfizer representation is the sinusoidal quantities with the same frequency can be combined by simple vector addition in the complex plane, transforming what would otherwise be a tedious trigonometric manipulation into straightforward geometry. When we combine phasors representing the voltage across different circuit components, we need only add them as vectors, automatically accounting for their phase differences, a process far more elegant than trying to manipulate the original sine and cosine function. So this phasor approach will become invaluable as we analyze increasing complexity AC circuits containing multiple components with different phase relationships. The rotating vector representation captures both magnitude and phase information simultaneously, providing a powerful visual and mathematical tool for AC circuit design. So to calculate the RMS root mean square value of the sinusoidal current, a quantity that repeatedly in AC analysis and represents the equivalent DC current that would produce the same power dissipation. We follow a four-step procedure that reveals the mathematical essence of this important quantity. First, we graph the instantaneous current I versus time, observing how it isosceles sinusoidally. Second, we square the instantaneous current at each point in time, creating a squared which is always positive. Third, we calculate the average or mean value of I squared over one complete cycle, denoted as the angle brackets enclosing I squared, which removes the time dependence and give us a single number. Finally, we take the square root of this average value at the RMS current, written as a subscript RMS, which has units of amperes. The RMS values has the profound advantage that for sinusoidal quantities it equals to the peak amplitude divided by the square root of 2, approximately equal to 1.414, which making calculations much simpler than working instantaneously values throughout. This RMS framework extends to voltages as well as allowing us to compare AC and DC systems on equivalent power bases. For sinusoidal AC sources, the RMS current and voltage values can be calculated using simple formulas derived from the definition we just discussed. The I subscript RMS equals the capital I divided by the square root of 2, and similarly the V subscript RMS equals capital V divided by the square root, where capital I and capital V represents the peak amplitude of the sinusoidal current and voltage. To illustrate this concept concretely, consider a typical wall socket in North America. It has a voltage and amplitude of capital V equals 170 volts, meaning the voltage alternates between positive 170 volts and negative 170 volts as it isolates sinusoidally. So the RMS voltage at that second is calculated as 170 divided by square root of 2, which equals approximately the 120 volts, the familiar voltage rating we encountered on appliance labels throughout North America. This distinction between amplitude, the 170 volts, and the RMS of 120 volts is crucial because Electrical standards, appliance ratings, and power calculations universally employs the RMS rather than the peak amplitude. When an appliance specifies the 120-volt voltage, it refers to the RMS voltage, not the peak voltage. And all power calculations use RMS current and voltage to determine energy consumption. Understanding this relationship between peak amplitude and RMS values is essential for practical electric and safety. When a resistor is connected to an AC source, the voltage and current amplitude are related by this law, written as the capital B subscript R equals I times the capital R, exactly as with DC circuit. The remarkable property of a resistor is that the resistance or the capital R does not depend on the frequency of the AC source, whether the frequency is 1 Hz or 1000 Hz. The resistance remains constant at the same ohmic value. The frequency independence makes resistors the simplest AC circuit elements to because we can apply the Ohm's law directly with the peak amplitudes or RMS values without any frequency-dependent modification. In the phasor diagram, the voltage and current phasors for a resistor point in exactly the same direction, indicating that they are in phase with each other, meaning they reach their maximum and minimum values simultaneously. This in-phase relationship reflects the intuitive fact that current flowing through a resistor responds instantaneously to the applied voltage. When voltage increases, current increases proportionally with no time delay. The power dissipated in a resistor given by P equals I squared times R depends only on the current amplitude and resistance, not on frequency, making resistor purely dissipative elements that convert electrical energy irreversibly into heat. Moving on to a phasor diagram showing the voltage and current in a phase for a resistor in AC circuit, likely illustrating that both V sub R and I are at the same angle in the phasor representation. The phasor diagram visually demonstrates for a resistor in an AC circuit the voltage across the resistor, the V subscript R, and the current through it are perfectly in phase, with both phasor pointing at the same angle from the reference axis. The horizontal placement of these phasors at angle 0 degree indicates zero phase difference, a characteristic unique to resistive loads. If we express the voltage as V times T equals capital V times cosine of a omega negative T and the current as I times T equals capital I times cosine of the omega negative T, where both have the same phase angle, we see mathematically why the phasors align perfectly. This in-phase relationship is not coincidental, but flows direct from the Ohm's law. Whatever instantaneous voltage appear across the resistor produces an instantaneous current proportional to it, with no phase shift. When multiple resistors are combined with reactive elements like inductors or capacitors. This straightforward resistive behavior provides a reference point for understanding more complex phase relationship. The simplicity of resistor behavior in AC circuit makes them excellent element of this for dissipating energy and limiting current. Rules they perform identically in AC and DC applications. So next is shows voltage and current wavelength for a resistor, plotted as function of times demonstrating their identical and amplitude relationship. The time domain wavelength illustrated on this slide show how the voltage across a resistor and the current through it isolates together in a perfect synchronization of multiple AC cycles. Both the voltage waveform and current waveform complete their isolations at exactly the same time, crossing zero and reaching peaks simultaneously, a visual confirmation in a phase relationship we discuss through the phasor diagram and mathematical equations by observing the peak of voltage and current occurring at identical times throughout the plotted time, and we gain intuitive understanding of what in phase means. There is no time delay, no separation between the voltage driving the circuit and the current responding to it. This instantaneous response is possible because a resistor has no ability to store energy. It cannot accumulate electric charge like a capacitor or magnetic energy like an inductor. The amplitude of current at any instant is simply the instantaneous voltage divided by the resistance, following the Ohm's law with no complications. For students accustomed to DC circuits, the resistive AC behavior is reassuringly familiar, with the only difference being that the constant voltage and the current of DC have been replaced by sinusoidally varying quantities that maintain their ohmic relation at every instant. When an inductor is connected to an AC, the voltage and current amplitude are related by a new expression different from the Ohm's law. The capital V subscript L equals capital I times capital X subscript where the capital X subscript all represent the inductive reactance. The inductive reactance is formally defined as the capital X subscript L equals the omega times L, where omega is the angular frequency and capital L is the inductance measured in henries. The critical insight is that the greater the inductance and the higher frequency both produce greater inductive reactance, meaning the inductor becomes increasingly effective at opposing current flow as frequency increases. This frequency dependence is fundamentally different from resistive behavior. A resistor's opposition to current, its resistance is independent of frequency, but an inductor's opposition to current, or its reactance, grows proportionally with frequency. In these circuits where the frequency is zero, an inductor acts like a short circuit with zero reactance, allowing DC current to flow freely. However, at high AC frequencies, the same inductor effectively blocks current flow as reactance becomes very large. The physical mechanism underlying this frequency dependence is electromagnetic impact. As current changes more rapidly, higher frequency, the changing magnetic flux produces a larger induced voltage that opposes the current change more strongly. So moving on a diagram for an inductor in an AC circuit with a voltage and current phasor separated by the 90 degree, demonstrating the leading voltage-lagging current relationship. The phasor diagram presented here reveals the distinctive phase relationship for an inductor. The voltage across the V sub L subscript L leads to the current by exactly 90 degrees, or the pi over the torradians, meaning the voltage phasor points 90 degrees counterclockwise from a current phasor in the complex lane. Conversely, we can say that the current lags the voltage by 90 degrees, which is the same statement expressed differently. The current reaches its peak 1/4 cycle after the voltage reaches its peak. Mathematically, if the voltage is expressed as V times T equals capital V times cosine of an omega negative T, then the current is I times T equals capital I times cosine of omega T negative of, or equivalent capital I times sine of omega to negative T. So this 90 degrees phase shift is caused by the inductor's property of self-inductance. The induced voltage opposes changes in current, creating an inherent delay between the applied voltage and resulting current. The practical consequence is that in circuits with inductors, you cannot simply multiply instantaneous voltage and current to find power. The phase difference means that energy isolates between the source and the magnetic field rather than being dissipated, a phenomenon we'll explore in detail when discussing AC power. So this next slide displays the voltage and current waveforms for an inductor, showing the 90 degree 90-degree phase separation in the time domain. The time domain waveforms displayed on this slide make visually apparent the 90-degree phase shift between the voltage and the current in an inductive circuit. The voltage waveforms reaches its peak and crosses 0 1/4 of a cycle between the current waveform, thus a temporal separation that corresponds exactly by the 90-degree phase difference in phasor diagram. Tracing the curves from left to right, you can observe when the voltage is at its maximum. The current is just beginning to increase from zero. When voltage reaches zero and in its way downward, the current reaches its maximum when voltage reaches its minimum. The current is decreasing back to zero, and finally when voltage completes its cycle returning the maximum, the current is at its minimum. This continuous phase separation throughout an isolation reflects the inductor's continuous opposition to current changes. The magnetic field with the inductor stores energy and releases it in a way that consistently delays the current relative to the applied voltage. For a student learning AC circuits, this phase shift is crucial. It explains why series inductors in a circuit produce currents that lag the applied voltage, and it demonstrates that circuit analysis in AC requires attention to phase relationships, not just amplitude, magnitude. The 90-degree separation is exact and unchanging across all frequencies through the magnitude of the reactant changes. So when a capacitor is connected with an AC source, the voltage and current amplitude are related by capital V equals the capital I times capital X subscript C, where capital X subscript C represents the capacitive reactance, defined mathematically as capital X subscript C equals 1 divided by the omega times capital C. Here, The omega is gained in an angular frequency and capital C is the capacitance measured in farads. The crucial observation is that the greater capacitance and higher frequency both produce smaller capacitive reactance, meaning the capacitor becomes increasingly transparent to current flows as either capacitance or frequency increases. This behavior is opposite to inductors. While inductors' reactance increases with frequency, capacitors' reactance decreases with frequency, approaching infinite reactance, complete blocking at zero frequency or the DC, and approaching zero reactance, perfect conductivity at very high frequencies. Physically, this makes intuitive sense. A capacitor is fundamentally a charge storage device, and higher frequencies provide more opportunity to charge to flow and to and off the capacitor plates. At DC, zero frequencies, no AC current flows because the capacitor fully charged and stop current flows. At high AC frequency, charge flows constantly by back and forth and the capacitor acts almost like a short circuit. The frequency-dependent nature of capacitance, a capacitive reactance, makes capacitors useful for application like frequency selection and radius, as well see when discussing the circuit. Next is the diagram for a capacitor showing a voltage and current separated by the 90 degree sweep current leading voltage. The phasor diagram shown here demonstrates the distinctive phase relation for a capacitor. The current to the capacitor leads the voltage across it in V subscript C by exactly 90 degrees or the pi over radians. Notice that this is opposite to the inductor's case. Equivalently, we can say the voltage lags the current by 90 degrees, meaning the current phasor points 90 degrees counterclockwise from the voltage phasor. Mathematically, if the voltage is V times T equals capital V times cosine of the omega into negative T, then the current is in I times T equals the capital I times cosine of the omega times T plus pi over 2, or equivalent to the negative capital I times sine of the omega t. This 90-degree phase advance occurs because a capacitor current depends on the rate of a change voltage, not on the voltage itself. The I times t equals the capacitance C times the derivative of V times t with respect to the time, or the t over v times dv times d. Since derivation differentiations advances the phase by 90 degrees in sinusoidal function, the current naturally leads the voltage amount the opposite phase shift compared to inductors. Current leads instead of lagging reflects their opposite roles. Inductors resist current changes, while capacitors facilitate them. This phase relationship has important implication for power flow and resonance phenomena in AC circuit. Next, this shows voltage waveforms for a capacitor with current wavelength leading to voltage waveforms in time. The time domain wavelength illustrated here visually, making it clear the 90-degree phase lead of current over voltage in a capacitive circuit. The current waveforms reaches its peak and crosses 0 1/4 cycle before the voltage waveform, thus demonstrating the current leading voltage temporally and spatially on the plot. Reading from left to right along the time axis, the current is at its maximum. Voltage is just the beginning to increase from zero when the current reaches zero On its way downward, the voltage reaches its maximum. When current reaches its minimum, the voltage is decreasing back through zero. And when the current completes its cycle and returns to maximum, voltage is at its minimum. This temporal relationship is inverted compared to inductors and reflects the fundamental mathematical relationship between the charge accumulation or the voltage and the charge movement or the current. Current represents how fast charge is moving and so on onto or off the capacitor plates, while voltage represents how much charge has accumulated, making current the time derivative of voltage approximately. For circuit designers, the capacitor's current leading behavior is valuable. Capacitors can be used to correct the excessive current lagging behavior caused by inductors, a technique called power factor correction used throughout industrial electrical systems. The consistent 90-degree separation between the current and voltage for capacitors, like the same relationship for inductors, provide a stable reference point for a circuit analysis regardless of the opening frequency. So the comprehensive graph displayed shows how the resistance of a resistor R and the reactance of an inductor, the X subscript L, P, and the capacitors X subscript C vary with angular frequency omega. Resistant R Resistance R is entirely independent of frequency, appearing as a horizontal line at a constant value on the graph. This fundamental property means resistors behave identically at the DC 60 Hz, EC, or megahertz frequencies. Inductive reactance, or the X subscript L, increases linearly with angular frequency omega, starting at zero when omega equals zero and rising infinitely as frequency increases, demonstrating that inductors are transparent at DC but become increasingly effective at blocking current at higher frequencies. Capacitive reactance, the X subscript C, decreases hyperbolically with increasing frequency, showing infinite reactance when omega equals zero, and approaching zero reactance as frequency approaches infinity. This comparative visualization reveals why circuit design work for particular frequency ranges. The low frequency limit where omega approaches zero, capacitors block inductors pass, making inductors vulnerable for DC power supplies, and low frequency filters conversely in the high frequency limit as omega approaches infinity. Inductors block and capacitors pass, making capacitors valuable for high frequency signals routing. So the point where the X subscript O and the X subscript C defines the resonant frequency of the circuit, a phenomenon of central importance in radio tuning and filter design. To understand how loudspeaker routes audio signals of different frequencies to the appropriate speakers, consider a typical speaker system with a woofer, a large speaker that would reproduce low frequency bass and a tweeter, a small speaker that reproduce high frequency treble sounds. So both speakers are connected in a parallel across the amplifier output, meaning they share the same voltage source but each carries its own current path, as you can see. So a capacitor placed in a series with a tweeter branch blocks the low frequency components of sound, preventing bass signals from reaching the tweeter, where they will produce distortion, while simultaneously passing the higher frequencies that the tweeter is designed to reproduce clearly. Conversely, an inductor placed in series with the woofer branch blocks the high-frequency components, protecting the woofer from attempting to reproduce rapidly isolation that would strain its mechanics and produce poor sound quality, while allowing the lower frequency to pass through unimpeded. This clever frequency selective design exploits the capacitor's property that reactance decreases with increasing frequency and in the inductor's property that reactance increases with increasing frequency. The result is a crossover network that automatically directs each frequency band to the speaker best suited to reproduce it, achieving superior and sound quality with a simple passive circuit. So this application beautifully demonstrates how understanding AC circuit element behavior directly solves practical engineering problems. When a resistor, inductor, and capacitor are connected in a series with an AC source called the LRC series circuit, the voltage and current amplitude are related by capital V, where capital V equals capital I times capital Z, where capital Z represent the impedance of the circuit. The impedance is calculated using the fundamental formula capital Z equals to the square root of the capital R squared plus the quantity of the capital X subscript L minus subscript C all squared all squared were written where the capital R is the resistance and the capital X L subscript is the inductive reactance and the capital X subscript C is a capacitive reactance. So this impedance formula is the AC analog of Ohm's law for DC circuits, just as V equals the IR relates voltage, current, and resistance in DC circuits. So V equals I. Z relates the voltage, current, and impedance in AC circuits. The impedance combine the effective resistance, which is frequency independent, and the reactance, which is the difference between inductive and capacitive reactance, and can be positive, negative, or zero depending on the operating frequency. So at the resonant frequency, X sub L is equal to X sub C. The impedance reaches its minimum value of C equals the capital R, a condition where the circuit draws a maximum current and behaves like a pure resistor. The impedance and its frequency dependence determines circuit behavior. At frequencies below resonance, capacitive effects dominate; above resonance, inductive effects dominate. And at resonance, the circuit achieves the most efficient energy transfer from the source to the circuit. Moving on to the impedance triangle diagram showing the relationship among the R, the X sub L minus the X sub C and Z. Graphical representations shown here, likely including the impedance triangle or the phasor diagram or resistance reactance impedance relate geometrically in an LRC circuit. If you imagine the resistance capital R plotted horizontally and the net reactance, the X sub L minus X subscript C plotted vertically, then the impedance capital Z forms the hypotenuse of a right triangle, with the angle phi between the impedance and the resistance giving the phase angle of the circuit. This phase angle phi determines whether the current leads or lags the voltage. When the X sub L exceeds X sub C, subscript C, or the inductive dominant, the phase angle is positive. The current lags the voltage and the current circuit behaves inductively. When X sub L exceeds X, X subscript C exceeds X sub L, the phase angle is negative. The current leads the voltage and the circuit behaves capacitively. And if when X sub L is equal to X sub C at resonance, the phase angle is zero. The current and voltage are in phase and the maximum current flows. So the tangent of the phase angle is X subscript L minus X subscript C divided by R, providing a direct relationship between circuit component values and phase behavior. So phasor diagram or abstract voltage phasors representing the voltage drops across each component, resistor, inductor, and capacitor, with the sum equaling the applied voltage phasor, demonstrating how individual component voltages can have different phases yet combine to equal the source of voltage. Next shows how frequency responds to curve RC circuit, or perhaps an example calculation demonstrating the impedance, the phase angle, and impedance changes with frequency. The slide facilitates understanding of all RC series circuit by illustrating how the impedance and phase angle vary with frequency, revealing the constant peak that characterize this circuit. So at very low frequencies approaching the DC or the capacitive reactance, X subscript C approaches infinity with inductive reactance the X subscript L approaches to zero. So making the impedance very large and the circuit primarily capacitive with current leading voltage. The capacitor effectively blocks the low frequency current at the resonant frequency or the F naught or the omega or P omega naught, where omega equals 1 divided by the equal root of the LC. So the inductive and capacitive reactance exactly cancel. The impedance reaches its minimum value equal to R, and the current reaches its maximum value with current and voltage perfectly in phase at very high frequency. Inductive reactance or the X subscript L dominates the impedance, making it very large and the circuit primarily inductive with current lagging voltage. So the inductor effectively blocks high frequency current. The sharpness of the resonance peak, its height and width. So let us first solve the problem solving about in an LRC series circuit, the RMS voltage across the resistor is 30 voltage, across the capacitor is 90 voltage, and across the inductor is 50 voltage. What is the RMS voltage of the source? So let us first know that in an LRC series circuit, the voltage across the resistor, inductor, and capacitor are not added directly because they are out of phase with each other. Voltage across the resistor is in phase with current. Voltage across the inductor leads the current by 90 degree. Voltage across the capacitor lags the current by 90 degree. Because of this, we must use phasor vector addition, not simple arithmetic addition. So let us first know the given. We have this one, V subscript R is equal to 30 voltage, V subscript C is equal to 90 degree voltage, and the V subscript L is equal to 50 voltage. Second is to identify which voltage oppose each other. So the inductor and the capacitor voltages are 180 out of phase with each other. So all we need to do is subtract them. The negative sign means the capacitor voltage is larger. Next is use the phasor voltage formula. So this is the phasor voltage formula. The RMS source voltage is given by this. So as you can see, after that, we need to substitute the given values. So all you need to do is substitute here and there and this. After you're going to substitute, you need to calculate. Then after you calculate, we're going to find the final answer, the 50 voltage, the RMS. So as you can see, even though the individual voltage across the component are quite large, the source voltage is smaller the capacitor because the capacitor smaller because the capacitor and inductor voltage partially cancel each other due to their opposite phase direction. This is a key feature of the AC circuit and show why vector addition is essential. So measuring the body fat bioelectric impedance analysis. So bioelectric impedance is a non-invasive medical technique that uses the principle of AC circuit to measure the body composition and determine body fat percentage in patient, as you can see. So multiple electrodes are attached to the patient, chest, and other body location. And these electrodes apply a small alternating current or the AC and of 50 kilohertz, which is sufficiently high to penetrate deep into the body tissue without causing discomfort. The attached instrumentation measures both the amplitude and phase angle phi of the resulting current flow through the patient body in response to the applied voltage, providing a detailed information about the electrical properties of internal tissue. The impedance Z of the body varies depending on the relative amount of water and fat along the current path. Because water, a major component of muscle tissue, is highly conductive or conducts current easily, while fat tissue is poorly conductive and presents much higher impedance to current flow since muscle tissue contains approximately the 70% water, while fat tissue contains only 10% water. So tissues with higher water content, more muscles, produces lower impedance values, while fatty tissues produce a higher impedance. By measuring impedance and using calibrated mathematical models, healthcare providers can calculate the patient's total body water, fat-free mass, and ultimately body fat percentage with reasonable accuracy, making this technique valuable for assessing obesity, monitoring weight loss programs, and tracking changes in body composition during medical treatment. So these practical applications beautifully demonstrates how the AC circuit principles studies in this chapter, impedance, phase relationship, and frequency-dependent behavior extend beyond laboratory physics to solve real-world medical and health problems. Start. So in a resistor connected to an AC source, voltage V and a current I are perfectly in shape. Both reach maximum zero and a minimum value simultaneously, as shown by the overlapping sinusoidal curves in blue and black. The instantaneous power, or the P times T, is equal to V times T times I times T, is calculated by multiplying these two in phase sinusoids form or the black form, as you can see. So the black curve, that is y positive never going below to zero. So this positive power means energy flow continuously from the source to the resistor where it is dissipated as heat. No energy returns to the source. The average power over one cycle is V subscript RMS times L subscript RMS, or equivalently to 1/2 times V naught times I naught, where V and I are the peak values. Unlike reactive element resistors consume real power continuously, making them only circuit elements that dissipate energy irreversibly. So the graph clearly show how the P times T isolates at twice the AC frequency, but remains positive, reflecting the quadratic nature of the V times I product in a phase sinusoid. These fundamental behaviors are used for heating elements, current limiting power dissipation in electronics, while in power injector, current lags voltage and V by exactly 90 90 degrees, as shown by the phase-shifted sinusoidal curve, or the black current lags blue voltage by 1/4 cycle. The instantaneous power, or the P times T to the power of, equal to V times T times I times T, isolates symmetrically above and below zero because V and I always have the opposite signs when one is positive and the other is negative. Negative power regions indicate energy flowing from the inductor's magnetic field back to the source. Positive power regions show energy flowing from source to the inductor. The power waveform isolates at twice the AC frequency with equal positive and negative areas, resulting in average power. P average is equal to zero. Resistors, pure inductors consumes no net energy. They only store and release magnetic energy. This zero average power explains why inductors don't get hot and dissipate energy irreversibly. The graphs clearly illustrate the energy isostatic rather than the dissipation. So in a pure capacitor, in a voltage V lag current by exactly 90 degrees, as shown by the phase shifted curves, or the blue voltage lags, or the black current by the 1/4 cycle. So the instantaneous power, or the P times T, is equal to V times T times I times T, isolate symmetrically above and below zero because the V and the I have opposite sign, with one is positive and the other is negative. Negative power occurs when V and I have opposite signs. Positive power when they have the same energy. So the power waveform isolates at twice the AC frequency with perfectly balanced positive and negative areas, yielding average power, or the P average. Like inductors, pure capacitor consumes no net energy. They only store and release electric energy. This zero average power explains why capacitors don't dissipate heat like resistors. The graph mirror the inductor's behavior but with reversed phase relationship. While in a general AC circuit combining resistor, inductors, and capacitors, voltage V and the current I have arbitrary phase angle phi between 0 degrees and 90 degrees, as shown by the phase shifted sinusoidal curve, or the blue voltage leads black current by the phi. The instantaneous power is equal to the V times T times I times T associate but has positive average power is equal to the one half the P average equals one half V naught the I naught cosine phi. So the phase angle phi determines the power factor or the cosine phi to the negative 1 for pure resistor and 0 for the pure inductors, capacitors, or the no power dissipated. So resistors contribute positive average power, elements contribute zero average power. So the power waveform shows larger positive areas than negative areas when cosine phi representing net energy transfer from a source to circuit. So the average percentage using the RMS values pronounced as the VRMS and the cosine phi this is the universal for AC circuit. So this explains utilities penalize low power factors circuits showing the same current but with poor power factor consumes more power from generators without doing useful work. So in this slide, it presents the universal AC circuit. So the power formula for any combination of resistors, capacitors, and inductors where the V across the circuit leads current by current I by phase or the phi. The power factor is denoted as the cosine phi, a dimensionless number between 0 and 1 that quantifies the efficiency of power delivery. For a pure resistors, the pi is equal to 0 degrees, the cos pi is equal to 1, and all the apparent power becomes the real power. The average power delivered to the circuit is the average is equal to 1 half V naught I naught cosine phi, where V naught and I naught are voltage and current amplitude. So equivalently, using the RMS values or the P is equal to P average is equal to the V RMS I then cosine phi. So the phasor diagram, as you can see, shows the voltage phasor decomposed into the V subscript R is equal to V cosine phi in phase with current or resistive component, and V um, subscript react is equal to the V sine phi 90-degree out of the phase reactive component. Only a resistive component contributes to the average power. Reactive components average to 0. So the graph plot resistance R in the flat horizontal line, inductive reactance or the X subscript L straight rising with the log, a capacitive reactance, the X subscript C or the hyperbola falling with a log, and the total impedance or the Z is equal to this square root of R squared plus close open parenthesis of X subscript O minus X subscript C square root versus the logarithmic angular frequency or the as frequency increases, the X subscript L increases linearly while the X subscript C decreases hyperbolically, crossing a crossing a resonant frequency, the omega naught. So where X subscript L is equal to the X subscript C and X subscript L minus X subscript C is equal to 0. So at this frequency, impedance Z reaches minimum value. X is equal to Z. Then after the X equal to R, so it's purely resistive, yielding maximum current for given voltage. So below is the omega net capacitive reactance dominant, and above is the omega net inductive reactance dominant. Then at resonance, phase angle phi is equal to 0 degree. Power factor cos pi is equal to 1 and circuit behaves like pure resistor. So this resonance phenomenon enables radio tuning, signal filtering, and efficient power transfer. Sharpness of resonance peak depends on the Q factor or the quality factor, then gives a narrower peak where it has become better frequency selectively. So resonance in AC circuit. So resonance occurs when varying the source angular frequency or the omega produces maximum current amplitude, the I at the frequency where the impedance Z is the minimum. So this peaking of current at a specific frequency is called the resonance. The resonant angular or the omega naught is where the current peaks at omega is equal to the omega naught inductive reactance or sub L. The X sub L is equal to the capacitive reactance and the X subscript C are equal. So X subscript L minus X subscript C is equal to 0 and Z is equal to R. So from X subscript L is equal to omega L and X subscript C is equal to 1 over the omega not C. And for LRC circuit, series circuit, this resonant frequency depends only on inductance L and the capacitance C, independent of resistance R. Resonance enables application like radio turning and just C to watch the omega not to desired station and bandpass filters. So as you can see, this graph shows current amplitude VI versus angular frequency with the omega for the LRC series circuit with V is equal to 100 voltage and L is equal to 2.0 hertz and C is equal to the 0.50 millifarad. And three resistant values, we have the 200 ohms, the 500 ohms, and the 2000 ohms. All curves speak sharply at the same resonant frequency or the omega naught, where the X sub L is equal to the X subscript C, but peak height, the sharpness vary dramatically with the R. Lower resistance or the 200 ohms produces the highest and the sharpest peak. Maximum current is larger and occurs over narrow frequency range, giving excellent frequency selectively. Higher resistance or the 2000 ohms produces lowest, broadest peak. Maximum current is small and occurs over wide frequency range or selectivity. Peak current is equal to the V over R since Z subscript min is equal to R at resonance. Peak height inversely proportional to R. Resonance sharpness quantified by quality factorial is equal to the omega naught L over R. Higher Q, lower R gives narrower, taller peaks. This explains radio turning variable capacitors adjust omega naught to match station frequency. Low R gives sharp turning to select one station clearly. So let us first have a problem solving. In an LRC series circuit, the source is operated on its resonant angular frequency. At this frequency, the reactance X subscript C of the capacitor is 200 ohms and the voltage amplitude across the capacitor is 600 voltage. The circuit has 3 is equal to 300 omega. What is the voltage amplitude of the source? So let us first have the given the capacitive reactance, the 200 ohms, the capacitor voltage amplitude, the 600 voltage, the resistance is 300, and the circuit condition is the resonance. Next, at a resonance in an LRC series circuit, the inductive reactance equals at the capacitive reactance, so their effects cancel. At resonance, XL is equal X subscript L is equal to X subscript C. The net reactance is equal to 0. The circuit behaves like a pure resistor. The source voltage equals the resistor voltage. So we will use this formula. Then after that, then we need to find the current amplitude. So the current amplitude, the voltage across the capacitor is related to the current by the capacitive reactance. So we need to solve for the current amplitude using this formula. Then after that, we are going to substitute the values. As you can see here, you have the 600 voltage over the 200 ohms. So we get this 3.0 ampere. Then after that, we need to use the resonance condition. So at a resonance, the source voltage equals the voltage across the resistor because the reactive voltage cancel. So we have this, the V source is equal to the VR. Then find the resistor voltage. So we need to substitute the values. We have the 3.0 ampere times the 300 ohms. So we get this 900 voltage. Then after that, so as you can see, here is the final answer. So let's remember that even though the circuit is at resonance, the voltage across the capacitor can be very large compared to the source voltage. This happens because energy isolates back and forth between the capacitor and inductor, while the source only needs to supply enough voltage to overcome resistance. The phenomenon is known as voltage magnification at resonance. Next is the transformers. So transformers consist of two coils. The prime, the N subscript 1 turns, then receiving the alternating current, the I subscript 1 from from an AC source, creating changing magnetic flux or the phi sub B in an iron core in an iron core which induce voltage or the V sub 2 in the secondary winding and in sub 2 that delivers power to a load resistor or the R. So the purpose of a step-up transformer as shown is to increase the voltage relative to the endpoint when the output voltage or we have this the V2 exceeds input voltage of the V1 while the current decreases proportionally to conserve power. The V sub 1 and the I sub 1 approximately equals to the V sub 2 and the I I sub 2. So the iron core maximizes magnetic coupling between primary and the secondary windings, ensuring nearly all flux from the primary links with the secondary for efficient energy transfer. So Faraday laws govern operation induced EMF or epsilon in each coil equals negative n times d phi sub b over dt. So V sub 2 over V sub 1 is equal to n sub 2 over the n sub 1. Then step-down transformers decrease voltage while increasing current used for distribution to homes. So transformers work only with AC because DC produces no changing flux sub B or the omega sub B and those no induction. So this voltage transformation enables efficient long distance power transmission to step up the generators and step down at consumers. In an ideal transformer, the secondary voltage or the V sub 2 to primary voltage or the V sub 1 equals the ratio of the number of turns in secondary coil or the N sub 2 to the number of turns in primary coil in N sub 1, expressed mathematically as this formula. So this relationship holds both voltage amplitude and RMS value, then making it universally applicable to AC circuits. So terminal voltage in a transformer refer to the voltage measured across the primary and the secondary windings when connected to an AC source and load. So if n sub 2 is greater than n sub 1, then V sub 2 greater than V sub 1, creating up the step up transformer that in that increases voltage while decreasing current proportionally. Conversely, if n n sub 2 is less than n sub 1, then V sub 2 less than V sub 1, producing as producing a step down transformer the decreases voltage that decreases voltage while increasing current. So this voltage transformation converses power because P sub 1 equals to the P sub 2 since V sub 1 I sub 1 approximately equals to V sub 2 and I sub 2 where I sub 1 and I sub 2 are primary and secondary currents. So the transformer assumption neglects losses like resistance and leakage flux, providing the fundamental design principle for all practical transformers used in power distribution and electrons. Now, let's go to the another problem solving. We have the phasors and alternating currents. You have a special light bulb with a very delicate wire filament. The wire will break if the current in it ever exceeds 1.050 ampere, even for an instant. What is the largest mean square current you can run through this bulb? So let us first notice the given. So the 150 A is the maximum allowable current, or the instantaneous, or the what we call the peak current. Then after that, in an AC current, the current varies with time. So the instantaneous current reaches a maximum value called the peak current, as you can see. So the RMS current is the effective current that produces the same heating effect as DC. For a sinusoidal AC current, we have this one. Then after that, identify what time limits the bulb. The problem tells us that the filament breaks if the current ever exceeds at 1.58, even for an instant. That means this value refers to the peak current, not the RMS current. So we have this, the I peak is equal to the 1.50 ampere. Then after that, we need to write the RMS peak current relationship. For AC current, the RMS value is related to the peak value by dividing by square root of 2. Then substitute the given value. You have this one, which we just only need is 2. Substitute. Then after that, we need to compute the value. Then after computing the value, this is the final answer. So as you can see, this means that although the current safely reaches a peak of 1.50 ampere, the effective RMS current must be limited to about 1.06 A to prevent the filament from breaking. Any larger RMS current would cause the instantaneous current to exceed the safe limit. Moving on to the fourth and last problem solving, we have the resistance and reactance. So a radio inductors, you want to the current amplitude through 0.50 mH inductors, part of the circuitry for a radio receiver to be 1.80 megahertz when sinusoidal voltage with amplitude 12.0 voltage is applied across the inductor. What frequency is required? So first we have the given, as you can see. Then after the given, we need to analyze for an inductor in an AC circuit. The opposition to current is called the inductive reactance. So denoted by X subscript L, the current amplitude depends on how the large this reactance is. So the formula we need are this one. Then after, we need to express inductive reactance. So since the current depends on reactance, we first relate the current amplitude and voltage amplitude. So we need to rearrange this. Then after arranging this into this formula, we need to substitute the given values. This means that the inductor must have an inductive reactance of about 600, 6,670 ohms. Then after, we need to relate the reactance to angular frequency. Inductive reactance depends on angular frequency. So solving for angular frequency, we need this formula. After that, all we need to do is to just simply substitute this one to this one, and L to the other one on the bottom part. Then after we substitute, we need to convert angular frequency to ordinary frequency using this formula. Then after we convert, we have this solution to convert the angular frequency to frequency. So after that, the final answer is this one. So this frequency lies in the radio range, which explains why inductors like these are used in radio receivers. So at this frequency, the inductive reactance limit the current amplitude to the desired safe value of 1.08 MHz. So, in conclusion, Chapter 31 brings together the essential ideas behind alternating current circuits, showing how voltage, current, energy, and power behave in a system driven by sinusoidal sources. Through concepts such as reactance, impedance, resonance, and power factor, the chapter explains both the theory and the practical operations of AC systems. These principles are not only central to understanding electrical isolations and circuit behavior, but also form the foundation of modern technologies, including power transmission, communication systems, and biomedical application. Mastery of AC circuit through theory therefore equips students with the analytical tool needed to understand, design, and innovate in real-world electrical and engineering systems. So that's all, and thank you.